I'd like to introduce the first speaker, Dr. Justine Nasejje. So Justine did her undergrad at Makerere University in Uganda. She subsequently did a postgrad diploma in mathematical sciences at Ames in Cape Town. She then came here to UKZN where she did her MSc and her PhD in biostatistics. You might recognize her. Last year she was the winner of the Kambule Award for the best dissertation. She is now a lecturer at Wits University in the Statistics and Actuarial Science Department. And a final fact, she's the mother to two beautiful twin girls of 7 months. So please join me in welcoming Justine.
Good morning, everybody. I'll be talking about the work I did, some of the work I did in my PhD research. And as he mentioned, I was working in biostatistics, so this is related to the biomedical type of research. So we used conditional inference forests, and we modeled time to event data or survival data. And what we had was survival data of children that were under the age of 5 from Uganda, and we got it from the DHS website. And then we also managed to get data of individuals that had extremely drug-resistant TB, and we're from 3 hospitals within South Africa. I think it was Gauteng and Northern Cape and Western Cape, if I'm not mistaken, but yeah. So why did we choose to use trees? Of course, it's one of the problems that we have, that we had, for example, in the Ugandan data set, we had around, it wasn't like really big, but we had around 6,000 children recorded in the data set I used for analysis. Well, there were about 10,000, but with the cleaning and, some of them really misrecorded records, we had to take out some of the things. So we ended up with around 6,000. So we basically chose to use the trees, partly because of that large data set, because it couldn't run with the usual methodologies that we're using at hand. And also some assumptions that are related with the models that we're using, for example, the Cox pH assumption. With the Cox pH model, we had a pH assumption which we couldn't necessarily forego or just underlook, and some of our covariates had such issues. Okay. What is the tree? And yeah, basically, if that's all of us, we can literally split the data into male and female. That is, if that's the optimal feature that separates this group. And we continue with the other features, for example. So for the males, you may find that there are other things maybe that separate the group even further. So it could be level of education, place of residence, and so on and so forth. Okay, so you can continue and grow a large tree and then decide, okay, maybe I've just done too much of the splitting, maybe let's prune back and have maybe an optimal tree at some point. So there are different methodologies that we can do to arrive to what we may consider an optimal tree. And a tree has been considered to be very unstable, so many researchers have recommended that we grow an entire forest. And work by Ziegler and Bremen actually is the one who documented who has a very nice documentation of a forest algorithm. Okay. A random survival forest is a special type of forest because we have data that is not fully observed, or that is not, we can use the word incomplete. Okay. So we have an event, we have some observational study And then we see that, okay, we're looking for some event of interest. So sometimes we may not necessarily observe that event due to time constraints and maybe costs and so on and so forth. Sometimes it's a dropout. Somebody leaves the area and whatever we are observing leaves the area, or we can't observe it anymore. And so we come up with that kind of data, and using the usual regression methodologies becomes a problem. Well, we may not necessarily use them. Okay, so we are therefore have to think outside the box, and we have the special type of trees, special types of methodologies. I mentioned about the Cox pH model, but in this case, we use the Cox pH models, and then we also use the survival trees. And what you do with the survival tree, you literally select a subset of covariates from a set of features or covariates, and you compute a measure, an impurity measure, to help you determine on which feature to split on. And then you choose a feature that has the largest significant value for the impurity measure. And then there you have the two nodes. And then you will repeat that until, for survival data, we literally look at a certain number of events that are within a node, and then we stop. Okay, but there are other stopping criteria as well. Okay, and one impurity measure is the log rank, and this has been used for many years to literally compare survival distributions. If you have two groups, you would calculate the impurity measure as described, as shown on the screen, and and that would help us look at it. It's literally a test statistic, and therefore we look at how large is it, how significant is it. If it is really large and significant, therefore we decide to the feature with the largest log rank statistic is the one that we decide to split on. Okay, so we can use the scores. The scores are good because if we have ties in the data, then we find it makes much more sense to use scores than the log rank statistic itself. Okay, and again, the best split is the one that maximizes that measure over all the possible splits. Okay, and the algorithm for the forest is literally to grow many of such trees, and we draw a B. We draw B. B is just the number of the number of bootstrap samples you want to get from your data, and usually mathematically it just goes to the 30% out of the bag. The OBB means out of the bag, and then you use 70% to train your data. There's a nice mathematical expression that brings us to have the 30% and maybe the 70 for training. Okay. So you grow a survival tree for each of the bootstrap sample, and then you grow the tree with that kind of constraint, because we don't want to literally have pure nodes, because we would literally struggle with the predictions. And then we can choose what to use for prediction. We can use the cumulative hazard function, or we can use the Kaplan-Meier curves. And then to obtain the forest prediction, we literally average the prediction value over the entire forest, or over all the trees that we've used. Okay. And the OBB, those that are left out when we're doing our bootstrap, we use them to look at the prediction error from our model that we've trained. But of course, this model has its own shortcomings, and one of the researchers says it has no concept of statistical significance, and so cannot distinguish between a significant and an insignificant improvement in the information measure. So hence the birth of what we call conditional inference forest. So before we do the split, it literally looks for an association between our outcome variable and the features or the covariates at hand, and then it goes ahead to determine the split based on determine the split on the covariate that we chose or the feature we chose from the splitting, from the association, from looking at how the outcome is associated, how strongly the features are related to the outcome. And then we repeat that, the step 1 and 2, because we are growing a tree, and then we literally grow a forest. Okay, so the difference between conditional inference forests is that, okay, we have to do an association test of all covariates to the survival outcome using a linear rank test. And in this case, we use the log-rank score to derive the linear rank test. And then the covariance with the strongest association to the survival outcome is selected for the splitting. And then for model evaluation, we use the Brier scores that are looking at the observed, the difference between the predicted, if we use the survival curve or survival probabilities as the prediction in the final node or terminal node. Then we will look at 0 if they are dead, then we subtract the prediction from the node, the survival probability prediction from the terminal node. And then if they're alive, we use 1 and then get that squared distance. The rest is just the weighting to take care of the censoring that is within the data, because not all individuals were observed. And we can use the integrated Brier score, and this is what we used in here, and then we used some form of cross-validation to make sure that there is no overfitting in our model. The model is not overfitting our data. Okay, so it is something we really observed that usually in biomedical research, people are just taking the random forest algorithm and using it on their analysis and forgetting that there is that bias that if you don't really test that strong association between the outcome and then the features, you're likely to always split at features that had the many levels of splitting. So it's a general bias. Many researchers have written about it. And because the conditional inference forest does that extra, or the first step and then the first step of testing for association, and then we do the split, we had to do a simulation study to literally establish that. Then the people in biomedical research can be guided, because any extra information that you have can literally save a whole bunch of people. So we literally simulated data sets. These are some of the data sets we simulated, and we used 2 different frameworks for simulation. I didn't talk about them here, but then we did for binary, so because maybe you have male and female, so we had more of those kind of features in that data set. And then polytomous, we just literally looked at features that had more than many levels, for example, including even continuous predictors in there, or even up to 4 levels if we did a categorical one. And then we also used interaction, we put some interaction terms in there. And here are the results. So you could see that with the binary covariates, still the conditional inference forest is having some improvements in performance when you compare. But of course, when I look at the first graph there's not really so much difference. So, and then when the more we increase the number of levels in the features or make them have more levels or more splitting points, we see that the conditional inference forest is gaining much more predictive performance. And it's just to show you how well it's working when we have features that have many split points, or even with interaction terms. And we did that on our two real data sets that I explained earlier. One was for the survival of children under the age of 5 in Uganda, and that literally, if I can just show you how it looks like, it has majority, of course I just took a few of them, majority of them had like many levels of one can, when you put in the tree algorithm or even the forest algorithm, they will definitely choose, for example, if you look at the sex of the child, you'll find the type of place of, the wealth index may come top as a feature to split on. And not necessarily because it's strongly associated to the survival outcome, but because of that inbuilt bias that is within the model. And this is the data set from the patients with extremely drug-resistant TB. It was generally full of binary kind of features. And those are features that, well, I don't think I was intending to really put this, but what I wanted to show that, okay, the results were somehow different when you compare to those from the forest, the conditional inference forest algorithm, for example. And this is the one on the real data, one of the real data set, sorry, the two sets of the real data sets that we used. And you could see that with the data sets with many, with features that have many split points, you could see a very big difference in predictive performance when you compare to the ones that are just binary in nature. So our conclusion was that, okay, conditional inference forests are desirable when we have a data set that has features or covariates with many split points. And our results were published in one of the articles in 2017, and those are the references. Thank you very much.
Thanks, Justine. Could you just explain a bit more detail when you were saying that trees are, the instability of the trees versus the random forest? Are you talking specifically of your survival scenario, or are you talking more generally than that?
Yeah, more generally, because each time you run a tree, you're likely to have a different sort of result. So generally, they advise to use a forest because when you're getting that prediction, you're going to average over a number of trees, and that stabilizes your prediction. Yeah.
Can you just explain a bit more about how the missing data in your case influenced the bias, introduced bias, in your data set? And then I know you handled it with the covariates thing, but I just want to have a little more understanding of how that missingness has to do with the bias that was introduced.
In my case, literally ignored the missingness, and that's why I said at the beginning, when I was doing the data cleaning, I excluded some of those because I had around 10,000. Yeah, so I did my analysis on only 6,000 cases, and so, but there are inbuilt algorithms in some of those packages, but I just didn't take that. My point here was just to look at the gain in the prediction performance if I have the two scenarios where I have features with many split points and those. So I didn't really care much about the missingness in the data.
I just want to ask how you handled your tree transversals. Like, were you able to do something like that?
Which one, sorry?
Tree transversal.
I have no idea what it is.
Okay.
Yeah. Can you explain? I think I'm here
I'm
to
talking
learn
about
as well.
the search pattern you used.
Oh, you mean the impurity measure?
Yeah.
Or I talked about it earlier. It was the log rank in case of survival analysis. But of course, I don't know if that's what it means. If I understand what you meant. If you can talk of the Gini index in other different. If it's I think the classification type of question, or you can talk about which other one? The entropy.
Hi, thank you for the talk. So if I understand correctly, this the approach. It's sort of like a classical machine learning approach. Are you looking at using more deep learning approaches? Because I'm aware of some literature that solve this problem for diabetes data using an adversarial approach to sort of learn by simulation. So I'm just wondering whether that's an area that you might be interested in going into, maybe looking at more deep learning approaches to model the time series data.
Yeah, so I'm looking at work I did from 2014. So I'm definitely now trying to literally dive into the machine learning techniques like the ones that are using here. So, and that's the reason as to why I'm here. So I'll look into that for my future research.
Oh, awesome. Thank you.
All right, I think let's thank Justine one more time.